All right, so cosecant is just the reciprocal of sine, right? So actually graphing it is not too tricky, it just looks weird. Okay, cosecant x is equal to 1 over sine x. So guys, be quiet. What's unique? Yeah, what's unique about these four graphs is that they all have vertical asymptotes. The reason being that, for example, for cosecant x, it's going to have a vertical asymptote whenever sine x equals 0, right? And sine x equals 0, do you guys remember where? Good. 0. When x equals 0 and also pi, 2 pi, etc., right? Every multiple of pi, sine x is going to equal 0. And so, when we graph cosecant, we want to make sure we have those vertical asymptotes. X and y equals cosecant x. So I'll have those in maybe red, I guess. We're going to have one vertical asymptote here at pi, and then 2 pi, 3 pi, minus pi, minus 2 pi. Okay? There are also some other points that we know. Because sine x is going to equal 1 at, you guys remember where?
0.
No. Pi over 2, 5 pi over 2, 9 pi over 2, right? And then sine x is going to equal negative 1 at 3 pi over 2, 7 pi over 2. Okay, and so that means we also, okay, let me do some tick marks. This is pi, this is 2 pi, this is 3 pi, minus pi, minus 2 pi. Okay, so at pi over 2, sine is going to be 1, which means that cosecant is also going to be 1, right? Because 1 over 1 is 1. And then at 3 pi over 2, sine is negative 1, so cosecant is negative 1. And so we have this alternating series here, like that. Okay? So a sine function would normally look like this, right? See how smooth my sine graphs are compared to yours, right? No, none of this stuff, right? All right. So, cosecant is actually going to look like this. It's going to be a bunch of u's that are infinitely long with vertically asymptotes. Even Mrs. Shack was complimenting for how good my sine graphs looked the other day. Okay, anyways, so you'll notice that cosecant has a period of 2 pi, right? Because it repeats itself every 2 pi. That also corresponds to the distance between every other vertical asymptote. And if I were to draw the corresponding sine function, it would kind of be like a almost tangent to these cosecant graphs, right? Oops. All right, so you need to be able to recognize these cosecant graphs.
It's a little pointy, especially at the second thing.
No, it looks good to me.
That's right. 3 pi over 2, that's pointy. That's not smooth.
No, it looks good to me.
3 pi over 2, take out pointy at it.
No, it looks good to me. Okay, so that's cosecant. And secant is very similar. It's just going to be shifted to the left. Same as secant. Same as the relationship between sine and cosine. So are we all good with this graph? Just look at the video later if you're not. Let's go to the next one. Okay, secant x. secant x is equal to 1 over cosine x. And it's going to be very similar, except all the vertical asymptotes are going to be shifted to the left. X and y. Instead of at pi, my vertical asymptote is now going to be at pi over 2, because cosine of pi over 2 is what? 0, thank you. Have you guys seen those videos of people on chalkboards doing dotted lines?
You do that?
Yeah. Yep.
Let's see it.
I train my. It's only chalkboards, right? But
You do it on a whiteboard?
no, it doesn't work because it requires friction.
I could help you on a whiteboard.
No, like the actual mechanism is friction based, so it's impossible on whiteboards.
Just use some less friction. You don't need that much friction.
I don't even think you know what I'm talking about if you think you can do it on a whiteboard.
So you're like,
Yeah, it's like.
whiteboard.
No, you can't. Okay, so secant, the graph of secant is going to look like this. Very similar. Everything's just shifted. Oops, that's too high. And these dips, they all happen at 1 and -1, right? So if I were to draw a dotted line here, this would be 1, and it would kind of touch every single, U at its tip. And then these vertical asymptotes, those occur at odd multiples of pi over 2. So here we have pi over 2, here we have pi, here we have 3 pi over 2, I'm not going to write it, and this is 2 pi, and this is 3 pi, this is minus pi, and this is minus 2 pi. Got it? This is 1.
So all the vertical asymptotes are in between pi and 2 pi.
Mm-hmm.
Why is that?
Okay. So I'll also draw what cosine would be on this graph. Cosine would just be this, right? That's, oh, frick. Why does it do that?
So is that how you draw such nice sign?
What do you mean? That doesn't touch. Screw it. Okay. So whenever you're confused about how or where to draw these secant and cosecant functions, just draw the cosine first and then draw the u's according to where the peaks and dips are. Okay? And then the vertical asymptotes are always going to be where cosine is equal to 0, right? So these vertical asymptotes, you see, they all occur at the intersections of the cosine graph with the x-axis. That's kind of a trick. Yeah. Okay, any questions?
So where would you like use this?
In real life?
Yeah.
I don't know. We kind of passed that point in like geometry, I think, right?
I know you can use like hyperbolas for like sound and stuff. Right?
Parabolas, yes.
Sound.
I mean, the graph of secant doesn't appear anywhere in real life, right? It's obviously not a real thing. Sine and cosine, on the other hand, are very physical. Okay, so that's secant and cosecant. Let's do some examples of how we might identify shifts vertically and horizontally. Sorry, stretches and shifts. So on Moodle, I have this document with 4 graphs if you want to refer to that. But otherwise, you can also just look here. Okay, so let's say I'm going to show you guys the trick for how to do this using methods we've already learned. Okay, let's say we're asked to find the function y equals a cosecant bx plus c. And we're given this graph. Okay. So the first step I would say is to find the period and then find b, which you guys all learned already. So here, what is the period?
1.
2 pi. 2 pi.
Times 2 pi.
2 pi because that's the distance over which it begins to repeat itself, right? And it's also the distance between every other vertical asymptote. So the period is 2 pi, which means that b equals 1. Thank you. B equals 1 because b is 2 pi over t, right? So b equals 1, no problems there. Now I shall show you how to find a and c. The general trick that I do is I go into this graph and then I draw where the original sine function would have been. And I do that by making it cross the x-axis whenever there is a vertical asymptote, and then making it touch the touch the cosecant graph tangentially. And then I find a and c based on this graph that I have. Okay, so clearly this is a negative sine graph with maximum 1 and minimum -1. So I know that a has to be -1. And then there's also no shifting going on vertically. So that means c is equal to 0 because the average is still 0. So my answer is y equals negative cosecant x, and I'm done. Okay, because this sine graph corresponds to y equals minus sine x. Yep.
What would you do if you didn't want a negative sign in the front?
Then I would have to shift it. I would have to do y equals cosecant x minus pi.
Now couldn't it also be cosecant x minus pi?
Did I just write that? Yes.
I was thinking about it, so I didn't notice you write it.
Okay, good. It could also be y equals cosecant x plus pi. Or x plus 3 pi, 5 pi, 7 pi, right? All the same. Okay, let me show you guys another one, a little more tricky. Nobody look.
Y equals secant x minus pi minus 2.
Noted. Noted. Okay, first step, what is the period?
Period is half or 1/2.
No.
1/2.
Period, anybody?
Sorry, 1.
2.
2, thank you. Okay, distance between over which it repeats itself, right? So that's clearly 2. Also this distance, or the distance between these two vertical asymptotes, also 2. So t is equal to 2, which means that b is equal to 2 pi over the period, which is equal to pi, right? So that wasn't too hard. B is just pi. Then my next step is I'm going to draw where the original cosine function would have been. So that would be here. So what is my quote-unquote maximum?
-3.
-1. And then what is my quote-unquote minimum? -3. Right? I'm basically just thinking about what's the maximum and minimum of that cosine function I drew in between. So what does that tell me the amplitude is?
1.
1. Right? That's just this distance, 1. And then what is the average?
-2.
-2. Okay? All I did was I found those values for this fake cosine function. So that tells me that A is going to be the amplitude, which is 1. And this is clearly a positive cosine graph, so I know it's positive 1. So that means that y equals secant pi x minus 2. Any questions? There will not be a quiz on this, but it will be on the test. The quiz,
So what's the next quiz on?
the next quiz is the same as the group quiz. Yeah, Joseph.
Where's the minus 2 from at the end?
The minus 2 comes from the average. So that's this line here. Guys, be quiet. That's the average, which is also the average, just the average of the maximum and minimum. Okay? We're not done yet. So cotangent and tangent left. Any questions about secant and cosecant? Pretty easy in my opinion. But then again, most of this is pretty easy in my opinion. Let's do cotangent and tangent. There are also vertical asymptotes here. Let's do tangent first. So tangent x is equal to sine x over cosine x. So, question, where would tangent have a vertical asymptote? Whenever cosine is equal to 0, right? So that tells us there's a vertical asymptote whenever x is equal to
0.
What?
2, 3, 4.
pi over 2, 3 pi over 2, 5 pi over 2, right? Those are all the values where cosine is equal to 0. You can check at home. So that tells us there's a vertical asymptote for tangent at those values, because cosine is 0. Where would there be x-intercepts? Where would tangent intersect the x-axis? That would happen whenever sine x is equal to 0, and sine x is equal to 0 whenever x is equal to 0, pi, 2 pi, right? All of those values.
Wait,
So,
is this still true on the unit circle? Like cosine
yes.
pi over 2 equals 0?
Yes. Uh-oh.
Is the vertical asymptote when cosine is 0?
Yep, because that makes the denominator.
When sine is 0.
Yeah, that's correct. So we would just draw this on our graph. Let's say, let's call this pi over 2 and this pi. That's spaced too closely together. Pi over 2, pi. So what's interesting about tangent and cotangent is actually they have period pi and not 2 pi. So that's very helpful, right? That's kind of confusing. Minus 2 pi, minus pi, minus 3 pi over 2. So first I'm going to draw a vertical asymptote at odd multiples of pi over 2. So minus pi over 2, pi over 2, 3 pi over 2, minus 3 pi over 2. Okay? And then I know that tangent also has to intersect the x-axis at even multiples of pi over 2, or multiples of pi. So that tells me that tangent is going to look like this. So make sure you're able to recognize this. Looks like seaweed. I don't know. Yeah, seaweed on the ocean floor. It's wavy. Okay, so notice how the period is not 2 pi, but it's actually pi, right? It repeats itself every pi radians. So that's very important. And it's going to change some of our equations. The reason it changes some of our equations is because now if we have tangent of bx, the period is going to be not 2 pi over b, but pi over b. And similarly, b is equal to pi over t.
Wait, what?
Because the period is not, the original period is not 2 pi anymore. The new period is pi of tangent. And so t is equal to pi over b instead of 2 pi over b. So I would advise memorizing that. All right. Shall we look at an example? We shall. Let's say we have this guy here. Nobody saw the answer. Okay. And it's asking you find the function y equals tangent of bx. So what is the period?
4 pi. 4 pi.
4 pi, thank you. The period is 4 pi because that's the distance between each vertical asymptote. It's also the distance over between every x-intercept. So the period is 4 pi, which tells us that b is not 2 pi over 4 pi, but pi over 4 pi, which is 1/4. And so tangent 1/4 x is our answer. That's a vertical stretch by a factor of 4, right? So that's tangent. And now cotangent can be found with a very similar process. I'm not going to explain it to you. You just know it. Okay, cotangent x looks very similar, so it's very easy to confuse, okay? But don't make that mistake. Cotangent x looks like this. I'm going to draw vertical asymptotes at every multiple of pi now.
Or wait.
Quiet, please. So the vertical asymptotes are now at multiples of pi instead of odd multiples of pi over 2, like for tangent. So this is pi, and this is 2 pi, and this is minus pi, and this is minus 2 pi. And so cotangent is going to go in the opposite direction. It goes from top to bottom. So cotangent is actually the same as tangent, except with a flip and a shift.
Your tangent lines are really good.
Everything I draw is very good.
It's better than your side.
Better than the 3 pi over 2 or whatever.
Yeah, no.
Yeah, 3 pi over 2.
All right, so notice the difference between tangent and cotangent. Tangent goes through the origin with a positive slope, and it goes from small to big, right? Goes with the, upwards. Cotangent, on the other hand, has a vertical asymptote at x equals 0, the y-axis. So it doesn't go through the origin, and it also goes from top to bottom, like that. Okay, very easy to confuse, so don't do that. And our same formulas are going to apply as well. So our period t is equal to pi over b, and b is also equal to pi over t. So not 2 pi, but pi. A final example, let's do this one. Nobody saw this. All right, so what is our period here for this graph? 1, thank you. Why am I always wrong? I don't know. So the period is equal to 1, because that's the distance between every vertical asymptote, right? And so the period is 1, which means that b is equal to pi over t, which is pi. And so y is equal to cotangent of pi x. Questions? Girls, stop talking to each other. Otherwise, you're not going to do well in this test. October 15th. October 15th. Next class? All right, so I want you guys to notice something, which is that tangent x is equal to negative cotangent x plus pi over 2. Okay? And I want you guys to show this using a graph, please. Well, I'll help you guys too. Okay. The reason is because,
Wait, tan x equals negative cotan?
yeah, Ginger?
You just reflected tangent, right, to get to a tangent, because it just faced the other direction, and then you shifted it.
That's right, yeah. So this identity is true because cotangent is just the flip of tangent along with a shift, right?
And then you shifted it over to the right.
This shift would be to the left, pi over 2, but it doesn't matter whether it's left or right in this case, actually, because it'll just be one more cycle over. So let me draw a tangent in blue. That goes upwards through the origin, right?
What's like the origin?
Yeah.
Okay? So that's tangent, and this is cotangent in red. Might be helpful to see this visually. Let me think. Well, I hope that's right. I've somewhat confused myself now.
No, that's fine.
This is pi over 2. This is 3 pi over 2. And this is pi. And this is, oh my gosh, what am I doing? This is negative pi over 2. And this is negative pi. And this is negative 3 pi over 2.
Are you gonna draw the asymptotes, or is that just too confusing?
It will be a bit confusing. Yeah. So as you can see, cotangent is just, so to get cotangent to become tangent, what we do is we first reflect cotangent and then shift it over to the left. Yeah? So if I were to draw minus cotangent in green, wow, this is going to be crazy annoying. If my minus cotangent x is in green, then that will be, this is like art now at this point.
Oh my goodness, what is that?
Oh. This is like Bob Ross.
Yep.
I'm not.
This one's a little ugly.
Oh, he made like diamonds. Like diamonds.
Oh, because it. Oh my goodness, that makes more sense.
Okay? And so, right, you can see now that tangent x is just minus cotangent x, but shifted over by pi over 2 to the left or right. So either works. And so that's how we prove this identity graphically. And you need to be able to differentiate between tangent and cotangent. Yeah, Joseph.
Is there going to be like a question like that on the test or quiz? Like proving
Just a test, just a test.
Maybe the practice test, but probably not the test.